Hello everyone, today I'm here to present my oral presentation, and then my topic is experimental and numerical verification of a slope sliding type isolation bearing, and I'm the presenter Lin Zhikuan, and my advisor is Professor Zhongli Lai. And this is my self-introduction. So first of all, I'm going to talk about why am I doing this research, and then later on I'm going to derive the equation of motion and also introduce the numerical method of our which we're going to use for the further discussion. And then in order to know our system thoroughly and then to comprehend the characteristic of our system, so we'll go through a parametric study. And then in order to know the feasibility of our system, so we'll go through a case study. And then we wish to verify our a numerical method and then to know the actual effectiveness of our system, so we'll go through an experimental study. And finally will be my conclusion. So we already know that a seismic hazard is always a great impact for not only to the foreign countries but also for Taiwan. So here are some few examples. And the first one will be the Chi-Chi earthquake happened in 1999, and then it caused 2,000 people died, and then 50,000 buildings collapsed. And then another incident is the Higashi Nihon earthquake, which is well known as the 311 earthquake, and then it caused the Fukushima Daiichi nuclear plant disaster. And then the last example is the Meinon earthquake happened in 2016, and then it caused the Weiguan Jingliang building collapsed, and also it caused $10 billion loss for the Southern Taiwan Science Park. So from these examples, we may know that facility breakdown may lead to a great impact to not only to the human safety, but also to the economy. Although the Taiwan Seismic Code had been improved to avoid the structure from major collapse, but however, the main structure will still has a risk of damaging under the earthquake. So it is important to improve the anti-seismic capability and also the ability to protect the important facilities. So isolation technique will be one of the solution. We already know that the isolation technique is an effective way to reduce the earthquake load transmitted to the superstructure. And then from the acceleration spectrum, we may know that if we lengthen or extend the structural period, then we may lower down the acceleration response. But meanwhile, as we extend the structural period, then we may also increase the structural displacement. So we'll need to increase the structural damping to lower down the structural displacement. So the isolation system will lengthen the lateral period by a sufficient flexibility. So here I'm going to introduce some isolation design principles. So first of all, we know that we need to have a sufficient vertical stiffness to support the vertical load. And then second, in order to lengthen the lateral structural period, so we need to have sufficient flexibility. And this is a schematic drawing for the lead rubber bearing. And then we need to have a sufficient energy dissipation mechanism to confine the isolation displacement due to what I just mentioned. If we lengthen the structural period, then we may also increase the structural displacement. So adding dampers is one of the most common used method to provide energy dissipation mechanism. And also, we may wish that our system to have a recentering capability. So one of the most common seen isolation bearing is a sliding isolation bearing. And then for the sliding isolation bearing, the energy dissipation mechanism is mainly provided by the frictional force. And then the sliding interface between the slider and then the sliding surface should be avoided by using a high friction coefficient material because it will take great influence to the characteristic strength. And then for the sliding isolation bearing, if it has provided the restoring force, then the shear force will be mainly provided by the frictional force and the restoring force. And then this is a schematic drawing of the hysteresis loop for the friction pendulum system. And from this diagram, we may see that the shear force will be mainly provided by the frictional force and then a linear restoring force. And here I'm going to introduce two conventional sliding isolation bearing. And first of all will be the pure friction system, which can be abbreviated to PFS. And PFS has a characteristic that it has a flat sliding surface, and it does not possess a specific isolation period. And also from the geometry may give us an idea that it does not have a restoring force. So PFS will has an advantage that it is insensitive to the earthquake, which is insensitive to the amplitude and the frequency content of the earthquake. But however, due to the lack of the restoring force, so it will have a larger residual displacement or also a larger displacement response under the earthquake excitation. And another conventional sliding isolation bearing is a friction pendulum system, which can be abbreviated into FPS. And then FPS will have a spherical sliding surface. And this is a schematic drawing for the FPS. And we can see that this is an articulated slider and then a spherical sliding surface with a unique curvature. So due to the unique curvature of the sliding surface, so the restoring force of the FPS will be a linear restoring force. And then also, the isolation period may only depend on the radius of the curvature. And the period may be written into this form. So from this form, we may see that the period is independent to the weight of the superstructure. And FPS will have the advantage that it has a better displacement control, and then it improves the recentering capability than the PFS. But however, it also sacrifices the advantage of the PFS, which has a specific isolation period, and then which may cause the FPS will have a resonant phenomenon during the near-fault earthquake or a low-frequency content earthquake. So if we wish to remain the advantage of both systems, then we need to have a solution. And then from my previous discussion may give us an idea that the geometry of the system should be avoided by using a pure flat surface or a unique curvature surface. So one of the solutions will be we wish the restoring force to be a nonlinear restoring force. But how? So in order to provide a nonlinear restoring force, the solution will be altering the geometry of the sliding surface. And then a slope sliding surface will be one of the solution. So here I'm going to introduce one new isolation technique, which is named as the slope sliding type bearing and can be abbreviated into SSB. And then this is a schematic drawing of the SSB system. And we may see that it has a sliding surface which has a small inclination angle. And then for the SSB, due to the slope sliding surface, then we will have a constant restoring force, which has a nonlinear relationship with the displacement response. And then due to the frictional force, so it may provide an energy dissipation mechanism. And here I'm going to move on to the derivation of our system. And before we start our derivation and then also the further discussion, here are some few basic assumptions. So due to the small inclination angle for our further discussion, so here are some few basic assumptions. The first one is that we neglect the pounding effect during the sliding motion. And then second is that we neglect the contribution of earthquake toward the normal force. And then third is that we neglect the vertical reaction projected by the horizontal earthquake. So first of all, we're going to talk about the single degree of freedom system. And here we assume the superstructure is rigid. So the mass of the superstructure is equal to m. And then F is represented to the frictional force. And then x2 double dot will be the ground excitation. By the Cartesian coordinate, then we may form up the displacement, velocity, and also the acceleration vectors. And then by these three vectors, then we may form up our equation of motion into this form. So from the equation of motion, we may see that the value of the restoring force may remain constant when the displacement is not equal to 0. So the relative acceleration of the system can be rearranged into this form. And due to the restoring force and the frictional force, and also the ground excitation can be seen as a constant value when the time interval is relatively small. So then the terms on the right side of the equal sign can be seen as a constant value b. And then if we integrate the b respect to t with the initial conditions when t equals to t0, that may lead us to get this form. And furthermore, if we substitute a t equals to t0 plus delta t, then we may get this form. So finally, we can form up the difference equation for our system with these coefficients. However, we haven't decided the frictional force for our system, so we'll first assume the k+1 step is in stick state, which represent that the velocity for the k+1 step will equal to 0. And then this condition may lead us to get a predicted frictional force. And then the actual frictional force may be decided by this form. And then here, the column friction model is adopted in our simulation method, which the value of the frictional force will remain in constant when the system is during the sliding motion. And then by the free body diagram and then the force equilibrium, then we may lead us to get the normal force of our system. But however, due to the small inclination angle of our system, so the normal force can be simplified into this form. And here we're going to talk about a 2 degree of freedom system. And first of all, we assume the superstructure is a single degree of freedom system, which the whole system will be a 2 degree of freedom system. And ms is represented as the superstructure, the mass of the superstructure, and mi is represented as the mass of the isolation layer. And then cs and ks will be represented as the damping coefficient and then the stiffness of the superstructure, respectively. And then again, by the Cartesian coordinate, then we may form up the displacement and then velocity and also the acceleration vectors for our system. And then by these vectors, then we can form up our equation of motion. But however, we haven't decided our frictional force again. So then we assume the k+1 step is in stick state. So by the velocity of the k+1 step is equal to 0, then this may lead us to get a predicted frictional force. And then the actual frictional force is again decided by this form. So after having the actual frictional force and then our equation of motion for our 2 degree of freedom system, then we may use the Runge-Kudam method for our simulation method. And then the Runge-Kudam method, which we adopt the tool of ODE 45 in the MATLAB. And then again, by the free body diagram and then the force equilibrium, then may lead us get the normal force of our system. But however, again, due to the small inclination angle, so the normal force can be simplified into this form. And then here I'm going to talk about the hysteresis loop of our system. So first of all, we may see that due to our slope sliding surface, so the restoring force, the value of the restoring force may remain in constant. And then later on, we may see that because we adopt the column friction model, so the value of the frictional force will be remain in constant as well. So finally, the hysteresis loop for the total base shear and the displacement response will be a twin flag hysteresis loop. And then the difference between each flag will be equals to 2 mu n. So now I'm going to move on to the parametric study. So first of all, in order to simplify the expression of the absolute acceleration, so we'll further neglect the higher order term of the tangent theta. So then the maximum value of the absolute acceleration can be expressed into this form. So we may see that the absolute acceleration is mainly influenced by the inclination angle and also the friction coefficient. But we haven't decided the influence of these two parameters toward the system displacement. And also, we may wish to know the influence of the external factor toward the system response. So we'll further discuss in a further discussion. So first of all, in order to know the steady-state response of our system, so we'll first exert a sinusoidal wave to our system. And then from this figure, we may see that the amplitude of the sinusoidal wave is gradually increased until it reaches our PGA goal. And then later on, in order to discuss the transient response of our system, so we'll further exert 5 different kind of earthquake records toward the system. And then this table will show the PGA for each earthquake. So now I'm going to talk about the relationship between the friction coefficient and then the acceleration response. So now if we look at the x-axis, we may see that it is a normalized friction coefficient. And then from the y-axis is an acceleration index, which can be represented as the absolute acceleration over the PGA. And then this index may indicate the effectiveness of our system, which when IACC is smaller than 1, then it means that the isolation system works. But however, if IACC is equal or greater than 1, then it means that the isolation system does not work. So now if we first focus on one line, then we may see that the greater the friction coefficient, then the greater the absolute acceleration response. And then if we further consider other lines, then we may see that the slope will be the same for the relationship between IACC and then the mu g over PGA for each line. And finally, the relationship can be expressed into this form. So this form may also explain why the IACC will have different y-intercept and also different turning points for each PGA. For PGA equals to 200 gal in an instance, then we may see that due to it has the smallest PGA, so it will have the largest y-intercept. And now if we look at the system performance under the earthquake records, then it may show that the previous relationship will still satisfy when the system is under the earthquake records. And then, so then we may see that the slope for each line will be the same. But however, the y-intercept for each line will be different. And then, especially for the Haga earthquake, it will have the lowest y-intercept. So again, from the previous relationship, we may know that due to the Haga earthquake will have the largest PGA than the others. So then it will have the smallest y-intercept than the others. So now I'm going to discuss the relationship between the inclination angle theta and then the acceleration response. So in order to ensure the system works under the earthquake, where theta varies from 0.5 to 5 degrees, and then with 3 different kinds of friction coefficient, so the PGA goal is set as 400 gal, and then the ground motion frequencies is equal to 2 Hz. And then from this figure, we may see that the IACC is smaller than the upper bound value 1, which implies the system works under the ground motion for various kinds of theta and friction coefficients. And besides, IACC will increase as theta increase in a linear relationship. From the relationship between the mu g over PGA and IACC, we know that the larger the friction coefficient, the larger the absolute acceleration. So from this figure, we may see that it will be a reasonable trend for a larger IACC with a higher friction coefficient. So based on the aforementioned experiments, so the relationship can be written into this form, which this equation may show that the linear equation will have a slope equals to this term, and then the y-intercept will equals to this term. So from the right figure, we may see that the scale for the x and y axis will be the same for these two figures. And then from these two figures, we may see that the relationship will still satisfy when the system is under the real earthquake excitation. And from the relationship between the theta and the IACC may shows that the linear equation of IACC will have a larger slope with smaller PGA. And a higher friction coefficient will cause a larger y-intercept of the equation. So here I'm going to talk about the relationship between the inclination angle theta and then the acceleration response. So in order to ensure the system works under the earthquake, where theta varies from 0.5 to 5 degrees, and then with 3 different kinds of friction coefficients. So the PGA goal was set as 400 Gale, and the ground motion frequencies is equal to 2 Hz. And then from the figure, we can see that IACC is smaller than the upper bound value 1, which indicates that the system works under the ground motion for various kinds of theta and then 3 different kinds of friction coefficients. And besides, if we mainly focus on one line, then we may see that the IACC will increase along with theta increase in a linear relationship. So, from the relationship between the mu g over PGA and IACC, we already know that the larger the friction coefficient, then the larger the absolute acceleration. So it will be a reasonable trend that the larger friction coefficient will have a larger absolute acceleration in this figure. So based on the aforementioned experience, then the relationship can be written into this form, which indicates that this term will be the slope for each linear relationship, and then this will be the y-intercept for each linear equation. And in order to know the performance of our system under the earthquake excitation, we'll see to the right figure. And then first of all, the scale for the x and the y axis are the same for these two figures. And then we may see that from this relationship may give us an idea that if we have a smallest PGA, then it will create a largest slope for the linear equation. And also, if we increase the friction coefficient, then the y-intercept will increase as well. So we may see that for the L central earthquake, which has the smallest PGA, then from the upper figure, we may see that it will have the largest slope than the others. And then if we compare these two figures, then we may see that the linear equations does has a larger y-intercept for a higher friction coefficient under the same earthquake. And now I'm going to talk about the influence of ground motion frequency toward the acceleration response. And first of all, the inclination angle is equal to 1.5 degrees in this figure. And if we mainly focus on one line, for example, when friction coefficient equals to 6%, then we may see that the IACC is uninfluenced by the various ground motion frequency. And also, it will remain in a constant value equal to 0.21. So this result will satisfy our expectation for this system, which it does not possess a specific isolation frequency, which remains the advantage of the PFS. And then, this figure may also shows that the higher the friction coefficient, then the higher the absolute acceleration. And the right figure is the system will have a constant friction coefficient equals to 6%. And then again, if we first focus on one line, then we may see that the IACC is uninfluenced by the various ground motion frequency. And also, the higher the inclination angle, then the higher the absolute acceleration. And now I'm going to discuss the influence of friction coefficient toward the displacement response. And then here I'm going to introduce a new performance index, which is named as the IDISP, which can be represented as the relative displacement over the PGA. And an IDISP is a normalized response of the system, which can be expressed as the maximum relative displacement over the PGA. And in addition, it has a lower bound value equals to 0 when the isolation system does not work. So from this figure, we may see that if we mainly focus on one line, then we may see that the displacement response of the system will decrease as the friction coefficient increase. And if we take all of the lines into consider, then we may see that the gap between each line will become smaller as mu g over PGA increase. But however, from the right figure, then we may see that the steady-state response under sine wave and then the transient response under the earthquake are quite different. So therefore, the system may not possess a straightforward relationship between the mu g over PGA and then the displacement response. But however, we may also see that the displacement response will generally decrease as mu increase until it reaches the lower bound value equal to 0. And here I'm going to talk about the relationship between the inclination angle and then the displacement response. So from this figure, we may see that the displacement response seems to have a nearly linear relationship with the inclination angle theta. So let's recall that the IACC will increase as theta increase in a linear relationship under the sinusoidal ground motion. So if we now maintain the PGA, so we suppose that the relative acceleration will increase as well. So this figure may show the maximum relative acceleration, and then we may see that the maximum relative acceleration will increase as theta increase in a nearly linear relationship. So by the approximate relationship between the relative acceleration and the relative displacement, then this may give us an idea that the displacement response will have a nearly linear relationship with the inclination angle theta. And then these two figures will show the system response under the earthquake records. And then this shows that the previous relationship won't satisfy the response during the excitation of the earthquake records. But however, we may also see that the gap between each lines will become smaller as friction coefficient increase. And also, we may see that the relationship between the inclination angle and then the displacement response is not monotonically correlated. For example, when a system is under the Kuma prior earthquake, we may see that the displacement response varies little when theta increase. So here I'm going to talk about the relationship between the ground motion frequency and the displacement response. So from this figure, we may see that if the x and y axis is in flow scale for this figure, then we may see that the displacement response seems to have a negative slope relationship with the ground motion frequency. So again, let us recall the relationship between the acceleration response and the ground motion frequency, which the IACC will remain in a constant value during various ground motion frequency. So if we maintain the PGA of the earthquake, so we suppose that the relative acceleration will remain in constant as well. So again, by the approximate relationship between the relative acceleration and then the relative displacement, that may give us an idea that the displacement response will be inversely proportional to the square of the ground motion frequency. And finally, I'm going to discuss the influence of the system parameters toward the residual displacement. So this is a residual displacement index, which can be represented as the residual displacement over the PGA. And then we may know that the system needs to satisfy the condition of tangent theta greater than mu to satisfy a perfectly recentering capability. And these values may show the value of the mu-G over PGA, which may lead the system to satisfy this condition. But however, by the x-axis, we may see that the system has already failed to satisfy this condition. But however, we can see that if mu-G over PGA is only slightly surpassed the boundary, then the system only has a little residual displacement. And then, when mu-G over PGA is around a 30 to 40%, then due to the variety of the earthquake force, then we may see that the system has a relatively small residual displacement under the El Centro and then the Haga earthquake, which these two earthquake happens to excite the system back to the original point. And then if we further increase the mu-G over PGA, then the system will gradually fail to work under the earthquake, so therefore it will remain at the original point. And from the right figure, we may see that when now the friction coefficient is equal to 6%, then the inclination angle needs to be greater than 3.4 degrees. But however, we may see that the system barely has a residual displacement when the inclination angle is around 3 degrees. So which indicates that the variety of the earthquake force will take a considerable contribution to the residual displacement. So here's my summary. First of all, the influence of each parameters toward the acceleration response is well known, which we know that the larger the friction coefficient or the larger the inclination angle will cause the larger the absolute acceleration. And the acceleration is insensitive to the ground motion. And then the system can accurately limit the acceleration response to meet the design target. And then finally, the system may not possess a straightforward relationship between each parameter towards the displacement response. So it may suggest that if we need to predict the displacement response of our system, it will be a better way to use the simulation method. So now I'm going to go through the case study. And first of all, there is a real isolated structure which is located in the Zhongshan district in Taipei. And by the location, then we can get the information from the Taiwan Seismic Code. And this table shows the basic parameters for the isolation structure. And now we're going to discuss our system with a conventional sliding isolation system, which is the friction pendulum system. And then before we start our discussion, and then we need to decide our design parameters for each system. And due to the fact that the SSB does not have a design procedure, so we'll now propose a simple design method for our SSB. And instead of designing the SSB to satisfy displacement requirement, it will be rather easier to let SSB to meet the absolute acceleration goal. And therefore, an absolute acceleration goal was set at 80 Gale, which is a divide of strong and medium earthquake reference to the Central Weather Bureau. And then, by the IACC index, we know that if IACC index is equal to 1, then it will be an index which indicates whether our system works or not. So then, by our design goal and the IACC equal to 1, then we can get this table, which each set of the parameters will satisfy our design goal. And then later on, we wish that our system to have a recentering capability, so then our system needs to satisfy the conditions of tangent theta greater than mu, and which may lead us to narrow down the design parameters. And then in order to have a sufficient energy dissipation mechanism, so we wish our friction coefficient to be larger. So then finally we may get our design parameters for our SSB. And for deciding the design parameters for the friction pendulum system, an optimal design procedures is adopted. And first of all, by the Taiwan Seismic Code and then a static analysis procedure that may lead us to get the effective stiffness and effective time period, and also the effective damping ratio. And then the only difference of our procedure to the conventional one is that we further adopt an optimal design procedure for the friction coefficient. So then we may get an optimal friction coefficient. And except for the 5 earthquakes we discussed in a parametric study, a near-fault earthquake, which is named of Taiwan Smart 1, is further considered in this section, which is recorded in the Wudong Station during the Hualien earthquake in 1986. And finally, we can get our design parameters for the friction pendulum system. So first of all, we'll discuss the influence of ground motion frequency toward the acceleration response and then the displacement response. So, for the friction pendulum system, it will have a resonant phenomenon while the ground motion frequency is close to the isolation frequency of the friction pendulum system, which equals to 0.26 Hz. And then this phenomenon may cause a relatively large absolute acceleration and isolation displacement for the friction pendulum system. And in contrast, the absolute acceleration of the SSB is uninfluenced by varying ground motion frequency. And besides, when a ground motion frequency is around 0.2 to 0.7 Hz, SSB not only has a lower absolute acceleration, but also has a smaller isolation displacement. And however, when a ground motion frequency surpasses 0.7 Hz, then we may see that the FPS will have a smaller absolute acceleration. And this result may imply that friction pendulum system may have a better result under the high frequency content earthquake. But nevertheless, two systems have similar isolation displacement when a ground motion frequency is higher than 0.7 Hz and will decrease as ground motion frequency increase. From this figure, we may see that the x-axis is the PGA of the earthquake, which varies from 0.2 to 1 Hz to 1 G. And from the figure, we can see that friction pendulum system is more effective on reducing the acceleration response under smaller PGA. But however, SSB will become more effective while PGA increase. As PGA equals to 1 G, for instance, SSB absolute acceleration is 44% of friction pendulum system. And the reason is because the absolute acceleration of SSB remains at a value of 80 Gal under each PGA. And instead, the absolute acceleration of FPS will rise along as PGA increase. And from the displacement response of the two systems, we may see that the friction pendulum system will have larger response for each PGA under El Centro earthquake, and the largest gap will occur when PGA equals to 1 G. And finally, this figure shows that SSB satisfies the goal of recentering capability, which will satisfy our expectation. From the figure, we can see that SSB is more effective on reducing the acceleration response since PGA is greater than 0.32 G. And due to the near-fault earthquake will have a low frequency content, so which may cause friction pendulum system will have a near resonant phenomenon. And then besides, due to the SSB may be sensitive to the low frequency ground motion, so we can see that SSB will have a larger displacement response than the friction pendulum system. And finally, this figure may shows that SSB still satisfies the goal of the recentering capability. And here's my summary. First of all, the two systems are both effective on their ground motion. And then later on, we can see that SSB is more effective when during a larger earthquake or a near-fault earthquake, and is functional under far-field or near-fault earthquakes. And the acceleration response of SSB will remain at a value of 80 gal. So now we already discussed the response of our system when it is a single degree of freedom. But how about if the superstructure is considered as non-rigid? So here we're going to use the design parameters which we determined in the previous section. And then here we'll first introduce a performance index, which is named of the superstructure acceleration index. And it is a ratio between the absolute acceleration of the system with isolation system over the absolute acceleration of the system which is non-isolated. And then from this figure, it may show that both systems is effective under the Taiwan Smart 1 earthquake. But however, from the right figure, it may show that SSB is more effective only when the PGA is equal to 1G. And unlike to the rigid case, we may see that the acceleration response of the SSB will not remain in a constant value of 80 gal. It will vary under different kind of PGA. And then FPS may have a more consistent result with the rigid case. And for the displacement response, we may see that the gap between the two systems will gradually increase, and the largest gap will occur when PGA equals to 1G. And here we may see that here's a shear index, which will be the maximum base shear of the system over total weight. And then from this figure, we may see that the shear index for the SSB will remain in a constant value. But however, for the friction pendulum system, it will gradually increase as PGA increase. So from these results, we may see that it does not show the benefit of our system. So now we wish to improve our SSB, but how? So one of the improved strategy is to alternate the design parameters, which we wish to sort out a solution to improve our system. And then first of all, if we may see that if we lower down the friction coefficient, then it may lower down the acceleration, it may lower down the absolute acceleration response of the superstructure. And also, if we lower down the inclination angle, it will lower down the acceleration response as well. And then for the displacement response, we may see that if we lower down the friction coefficient, then it will have a negative influence to the displacement response. But however, for some cases, if we lower down the inclination angle, it may also benefit to the displacement response. And for the shear index, we may see that if we lower down the friction coefficient, then it will lower down 34% of the shear index. And also, if we lower down the inclination angle theta to 1 degree, then it may also lower down 34% of the original shear index. And finally, from the left and right figures, we may see that the change of the parameters only slightly influence to the residual displacement. So now our target is to improve the effectiveness of the SSB. So in order to improve the effectiveness is by lower down the base shear. And in order to lower down the base shear is by lower down the system parameters. And also we wish that we won't sacrifice too much isolation displacement. So then the reduction of the friction coefficient should be reasonable. So finally, our new design parameters for the SSB is now determined. So this is the result of using the new design parameters of our system. So first of all, we may see that, let us recall that when a system is under the original parameters, SSB has a better results when PGA is equal to 1G. But however, if we look at this figure, it may show that SSB is more effective when PGA is greater than 0.6G, which shows a great advancement of the performance. And then, if we look at the displacement response, we may see that the friction pendulum system still has a larger displacement response than our system. And for the shear index, when using our new design parameters, it will lower down 49% of the shear index to the original. And finally, although we improve some performance of our system, but it may also sacrifice some of the recentering capability of our system. And if the system is under the Taiwan Smart 1 earthquake, then we may see that SSB is more effective under various PGAs. And then it may also, by using the new design parameters, it may also lower down the displacement gap between the two systems. And finally, we may see that our system, when the system is under the Taiwan Smart 1 earthquake, it barely has residual displacement. So here's my summary. First of all, by reducing the friction coefficient may only benefit the acceleration response. But however, if we reduce the inclination angle, it may not only benefit the acceleration response, and in some chances, it may also benefit to the displacement response. And suitable parameters will effectively lower the base shear of the SSB and achieve a better performance. And now I'm going to move on to the experimental study. So first of all, I'm going to introduce the shaking table experiment. And then this is a schematic drawing of our setup system. And this is the actual photo of the setup system. And then this is the actual photo of the slope sliding bearing. And then here are the accelerometers, and which have 3 accelerometers for measuring the X and Y and Z direction respectively on each corner. And then this is the load cell. And then this is the LVDT for measuring the displacement response. And then the total weight of the system is equal to 34.08 ton. And then we assume the superstructure is rigid in our experiment. And again, this is a schematic drawing of our bearing. And this table shows the design parameters of our bearing, and we may see that the inclination angle is equal to 1.5 degree, and the design friction coefficient is equal to 6%. And this table shows the earthquake records which we adopt in the experiment. And here are the PGAs. So, although the design friction coefficient is given, but if we use the given one, then we may find out that the simulation result shows quite different to the experimental result. So now we'll try to identify the friction coefficient by the experimental result. And this is a hysteresis loop of the system under the earthquake record. And we may see that although we neglect the pounding effect during the sliding motion, but on the result, we may see that the pounding effect during the sliding motion is unnegligible. So in order to prevent the pounding motion effect, the identification, so a displacement boundary of 25 millimeters was set. And then we pick 1.5 millimeters as an interval, and then we'll pick the maximum and then the minimum absolute acceleration in each interval, and which the red circle point will be our data point which we pick in each interval. So then by averaging each data points, then we may get a horizontal line. And then by our physical model, then we may know that the difference between each line will equals to 2 mu g if the y-axis is absolute acceleration. So then for a one hysteresis loop, then we may get a mu minus and then a mu plus for each hysteresis loop, if the positive and then the negative displacement response are both larger than 25 millimeters. So finally, by taking root mean square of all friction coefficient by all earthquake records, then we may get the friction coefficient is equal to 8.17%. So here I'm going to show our simulation result. And by using the friction coefficient equals to 8.17%, and then our inclination angle equals to 1.5 degree, and here we'll see the result of our system under the Kobe earthquake, which is a unidirectional earthquake. And first of all, the PGA of this earthquake is equal to 8.02 meter per second square. And then this is the relative displacement response. And then this is the acceleration response. And from the acceleration response, we may see that for both the simulation and the experimental results, it shows that our system does work under the earthquake excitation. And this hysteresis loop may show that our simulation result is quite fit to the experimental result. And this table will show the relative error between the simulation result and the experimental result. And if we first look at the peak absolute acceleration, then we may see that there is a relatively large error for the peak value. And this may be due to the fact that we neglect the pounding motion in our simulation method. But however, from the experiment, we may see that the pounding effect is unnegligible. So then it will produce a relatively large error. But however, if we look at the rooming square error for both acceleration and displacement response, then we may see that it has a relatively small error. And also for the peak value of the displacement response, it is quite small as well. So then it may show us that our simulation method is valid for simulating our system. And these are the hysteresis loop of our system under all the earthquake records which we adopt. And then from these hysteresis loop may show that the simulation results is quite fit to the experiment, and which prove that our simulation method is valid. So here are my summary. First of all, the result shows that the system is effective for both simulation and experiment. And then the simulation result of displacement response is quite accurate. And then third, the simulation result of peak acceleration response has much error due to the pounding effect in experiment, and it is due to the fact that we neglect the pounding effect in our simulation method. And finally, the simulation method works for presenting the dynamic behavior of our system. And the last part will be my conclusion. So first of all, the equation of motion and the numerical method was derived and introduced respectively. And second, the relationship between the system parameters, which are the friction coefficient and the inclination angle, with the acceleration response is well known. And then the acceleration response was proved to be insensitive to the ground motion. And third, the SSB is effective under a near-fault earthquake with suitable design parameters. And fourth, a simple design method is proposed to satisfy both the target acceleration, which we pick 80 Gauss at the first time, and also will satisfy our requirement for a perfectly recentering capability. And fifth is that our simulation method was verified by results of the shaking table experiment, and it shows that our simulation method is valid. And finally, the feasibility of our system is verified. So this will be my presentation for today, and thank you for listening.